why can I not individually address the 8 bytes that make up this pointer? Well, as it turns out, you can. So what we're going to do next is cast our struct into a byte buffer and actually individually access the bytes that make up this memory so that you can really see that everything is just an array of bytes underneath it. I want to share today a realization that when I had it, it genuinely changed the way that I look at programming and approach programming problems. And if you're already an experienced programmer, you might look at this stuff and say, oh, well, obviously. But I find but when I did not have much low-level experience, and when I was coming from a high-level programming language where all of this stuff is hidden from you, you never really come across it. And so once this clicks for you, you'll understand how file types are represented on the disk and how a .png image can suddenly become a little box in your image viewer, and also all the way from how network packets are transmit over the network and received and how everything is decoded, how programming languages represent different data types. To make sure that I prove to you that this is not just a random thing I'm making up, this is a technique that the Linux kernel actually uses right here in the IP packet parsing. Now, the thing that I want to get across to you is that everything is literally just bytes in the computer's memory. It's all bytes. No matter what kind of fancy abstractions we pile on top of it, it's all at the end of the day comes down to bytes. And so while like these different data types, they seem very discrete from each other. Like, think about this. How do you think that this struct is represented in the computer's memory? Now imagine if I was in a job interview with you and I asked you to give me the size of the struct in bytes. How much memory in bytes does that struct take up? You might be tempted to simply sum the size of the individual elements of that struct. And in the naive view, that is actually correct. But what's going to happen when we run this program? We're going to find something a little bit interesting. Now, the size of our struct in memory here, as you can see, is 32. But if you take the sum of these elements, which actually turns out to be 20, if you sum the individual elements in that struct, we get a size of 20 bytes. Yet, if we use the size of operator, it comes out to 32. Why is this? This is the naive view of how our struct would be represented in memory. So it's everything is just getting its own space that is the size of its data type. So if you take the size of a float, we say it's 4, so our first float is 4. Our characters are 6 bytes, so we've got 6. Our integer is 1 byte, so 1. Uint 8 is 1. The pointer on a 64-bit system is 8. And then the boolean is 1. And so this is what in the computer's memory we would expect it to be. Why is this not the case, and where does the extra 12 come from? Well, it comes down to memory padding and memory alignment. And what you'll notice is that if you actually hover over this with your LSP server, it'll actually tell you something very interesting. It'll say the size 4 bytes and then alignment 4 bytes. What's that? Especially if I hover over this one, you'll see 1 byte plus 4 bytes padding, alignment 1 byte. So what is padding and what is alignment? Well, as it turns out, that's where this extra 12 bytes comes from. This is what that struct is going to look like in memory with all of the padding fields applied. So why bother with alignment and padding anyway? It's all to do with how fast the CPU can access that memory address. The compiler wants to place all of these elements at an address that is a multiple of the individual element size. So for example, that's why when we hover over this float term, we get an alignment 4 bytes because it's 4 bytes in size. However, if we hover over this one, you'll see alignment is 1 byte, because each individual character in this array is 1 byte in size, and so the alignment stays at 1 byte. If we go to this pointer, you'll see we align at 8 bytes because the size of a pointer on a 64-bit system is 8 bytes. And so what we're doing here is once we get to this point in our struct with this U8 added, we're at 12 bytes. And you'll notice that 12 is not a multiple of 8. So what the compiler does is it pads by 4 bytes so that the starting address of this pointer is a multiple of 8. Now, over here at this boolean at the end, why do you pad 7 at the end to get us to 32 in total? We're up to 25 bytes here. Well, as it turns out, the alignment of a struct is based on the alignment of its largest alignment member, which in this case is a pointer, which is 8. And so what we want to do is get the total size of the struct to a multiple of 8, and to do that, we pad by 7. Now I want you to pay attention to the default initialized values in this struct. We've got a 0 float, the character's high, -1, a 4, and a false boolean. Now, what I've got down here is I've got a function that prints out raw bytes. So if you give it a byte buffer and a size, it'll just print out the individual bytes that make up that piece of memory. Now, I've also got two pointers down here. I've got a struct pointer, which you can address the members of the struct as you usually would, as you can see here with the arrow key. I've also got a pointer to anything, which is just a byte buffer pointer that you can cast to anything. And you can see down here, I have casted the struct pointer to an array of bytes, which will simply be the size of the struct, like I was showing you before. And the point of this is I'm going to show you that not only can we print out the raw memory that makes up this struct and show you what I was showing you in the photo editor just before, but actually print it on the screen programmatically, but we can also change and modify the members of the struct with both this arrow method as you usually would, but also by individually changing the bytes of memory that make up the underlying data structure. So we're going to first compile this, and I'm going to show you the printout of the struct. Now, if you look through this printout of the struct, you'll notice that we have a 4 bytes for the float, which would be 0. We've got H and I, this is ASCII high. By the way, if you're confused about the 10 here, this is to do with the representation of floats, which I'm not going to go into in this video. But for the simple ones, you can see this is H in ASCII, this is I in ASCII. We've got a -1 here because it's a signed integer, and we've got a 4 here, which is the unsigned positive integer, and there's a 0 like for the rest of it, which would be our null pointer and our false boolean. Now, what I do here is I change a couple things with the arrow method. I set the negative to -39, I set the float to 3.14, and I flip the boolean to true. Now, if we print out those raw bytes again, you'll see we've got a very different boolean, Now, if we print out those bytes again, you can see we've got a very different floating point number. We've still got high, but our negative has changed to D9, which is the hex representation of -39. And our boolean over here has flipped to a true. So what we did there was we changed the struct as we usually would, and we saw a direct change in the actual array of bytes that underlies that data structure. We can also address the underlying bytes directly. So for example, if I go to my byte buffer pointer and I set the byte at index 4 to a G, what do you think is going to happen when I print the value of the string from my struct with the dot method, as you usually would access struct members? Well, what's going to happen when we compile and run this is that we actually get GI instead of high. So what you saw there was we literally just changed the underlying byte, and it had a change in how our struct member access, as we usually would with the programming language, actually represents that string to us. And we can do the exact same thing with the negative value. So I change it directly using the offset to 10. And you can actually see the offset if you hover over it in your LSP. It'll show you what the offset of that struct member is. So you can access it directly. And you can see here we get -44, which is 0xd4 converted to negative. Now the natural question arises, can we go in reverse? We have seen a high-level primitive like a struct be transformed into a byte buffer, but can we take a byte buffer and convert it into a higher-level primitive like a struct or like a data type? The answer is absolutely yes, we can. And once you understand this, you understand everything, like how file parsers work, how network protocols are structured, how file types work, how files are stored on disk. Like, it all just comes once you understand this, which is we can take an array of bytes and provided it's in the right format, we can convert it into a high-level primitive like a struct or a data type or any other kind of representation you want, as long as that's defined. So what I've done here is I'm just setting our things we're dealing with to 0. So gMyStruct and gMyBuff. MyStruct is the struct we've been dealing with before. gMyBuff is just an array of uint8s, so an array of bytes. And what you can see me do here is I'm actually assigning the struct float to -9.29, and then I'm mem copying the 4 bytes, and you can see it's 4 bytes if you hover over the size of. I'm copying the 4 bytes that make up that float into this uint8 buffer. Now, what we're going to do next is pretty crazy, which is we actually cast the uint8 buffer to a float pointer, and then we dereference it and print it out with printf. You don't believe me that this is going to work? Well, let me show you. As you can see here, once we get to what's in my float buff after the mem copy, it is -9.29. So how the hell does that work? Well, as it turns out, once we do this memcopy, the 4 bytes that we see here that make up this floating point number, which this is, before we change it to 9.29, so this is not going to be what it actually is, but these get copied into our byte buffer. And then when we cast the byte buffer with no offset to a floating pointer, or any other pointer for that matter, it takes the first index of this, so like 0, right? It'll take 0th a memory address, and it'll say to the compiler, okay, you can use this as a float. And then we dereference it. And you can see this in action in the very next example. I say, what are the first bytes of these? If you cast our float from our struct to a byte buffer, and you print out the 0th byte, and you print out the 0th byte of my buff, you can see that they are actually the exact same. So D7 and D7. And we can print out the raw bytes that represent that float like this. And so you can see that with even data types in C, we can directly copy the underlying memory that makes that up and directly address it. It's actually really, really cool. Now, as promised, I'm going to show you an example of the Linux kernel using this technique. This is in ip.h. And what we're looking at here is a little helper function to get a IP header struct out of a buffer of bytes. And you look here, we've got a few definitions. We've got struct IP header, and this function returns a pointer to that. And it does this cast from skb network header. Okay, what's skb network header? skb network header simply returns an unsigned car array, or like a pointer to, a buffer of bytes. And so what we're doing here is we're taking this network header helper thing, which returns a pointer to a byte buffer, and we are casting that to a struct, which is, drumroll please, this one, struct IP header. And you can see we've got all the fields that are present in this. We have IHL, version, TOS, we've got TTL, we've got the source address and the destination address, and you can see it's the same as this. And we have the sizes of all of these that match up, and basically the realization from this is the realization. It's like, what we're doing here is we've got this struct with all these members that we can address in the programming language, like C. We can do, for example, IP header, comma, source address. And then we can actually use that for stuff. And the realization is, oh, well, this is just coming in as an array of bytes. And what we do is we just cast to the struct, and now all of a sudden we can do things with that. Like we can do if statements on the source address. We can do if statements on the protocol version. It's actually like a really cool realization to have. Now, if you're an experienced programmer, you will have realized there is an elephant in the room I haven't addressed yet, no pun intended, and that is endianness. So we're all having so much fun doing our casts. We're casting to byte buffers, we're casting to structs, we're casting data types, but endianness is here to ruin our fun. Endianness is a differing in byte order that bytes are stored in memory between different systems. And for example, we have little endian here and big endian on this Wikipedia page to demonstrate that for us. On little endian, we take the same 32-bit integer, and it's represented as 0D, 0C, 0B, 0A. Now on a big endian system, that same integer is stored as 0A, 0B, 0C, 0D. Now think about that. If we take that raw buffer and we cast it to an int on these different systems, they're going to get a completely different integer. So that's not going to work. And that's why, for example, the network byte order is an important thing. And so if you ever call like htons, htonnal, etc., it does all of this byte swapping for you. As far as I'm aware, from what I remember, big endian is the network byte order. And so when your computer sends out IP packets, it converts it to big endian automatically. But if you're on an embedded system or something like that, and you're communicating over UART and you just send a raw struct to another microcontroller, you need to check the endianness to be sure, and the receiver or the sender may need to do byte swaps on the fly before you can cast that data structure. The final example we're going to walk through is actually going to show you byte swapping on the fly like I just mentioned, and it's going to be checking out the header of this PNG file and seeing if there's anything interesting in there using our struct cast method that we just talked about. I've defined these two structs to try and match the size and the format of this example PNG header that I found on the internet. Now again, this does not actually account for the complexities of the PNG format. This is just an example, so put down your pitchforks. So what we have here is we try and match these fields. So the signature is a uint64, the header length is a uint32, the chunk type is a uint32, and then we actually have the header chunk itself, which is this, we've got the IHDR chunk that we can look at and see these sizes here. And so what we're going to do is read the header of this file directly from the .png, and you can open that in a hex editor to see what that looks like if you want. We're going to try and read this information right here, and we're just going to cast it to a struct and see if we can get the properties of the image. Now, this image that we're looking at is 1087 by 1080. So if we can extract that from the header, I'm going to be calling that a win. If you're wondering what this attribute packed means, it simply tells the compiler to remove the padding bytes that I explained earlier on in the video, at the cost of performance due to memory alignment issues. But this is necessary for our struct in memory to exactly match what our header is going to look like. Okay, so this part of the code is doing a very quick and dirty open and read of the file. You can see here I'm fopening it with a file pointer, I'm freading as you usually would to read a file in C, and then I'm printing out the raw bytes that are in that header that we've extracted. Then I do a cast, and I'm going to extract certain values of that. So for example, the PNG signature magic that we were talking about before, the type of the chunk, and the size of the chunk. Now, what I'm doing here also is this byte swap stuff to account for the difference in endianness. So the way that the PNG file is stored on disk, the endianness is different than what my computer is expecting when it actually does operations on that, for example, printing it as a decimal. And so if I go ahead and run this, you can see here, we print out this raw magic of the PNG, and you can see here when I print out that hex value, directly accessing that with my struct after I cast it, we're having the exact same thing as before. So I can see the chunk size is 13, the chunk type is IHDR in ASCII, and what I can go one step further is I can check if the chunk that we're expecting is the IHDR chunk, which contains the width and the height, and then I can simply print out directly what that is. Now you can see the size here is correct. This is what my PNG is, but if I take out the bswap, let's not account for endianness, and let's see what that does to our values. What we're going to get instead of our image correctly sized is we're going to get an absolutely ludicrously large image, because if you think about what the bytes are doing, if you've got like all the low bytes down here and you flip them to the other side, that's going to turn out to be a very, very big number. So there you go, guys. What we did there was we just extracted directly the PNG header information, and now we can access it. Like, if I want to do operations on that PNG file, I can simply call the struct and then dash height, and I've got it. It's pretty cool. It's really cool. I hope you guys really enjoyed this video. This revelation kind of changed the way that I look at programming and I think about memory, and it's really hidden from you in high-level programming languages where everything is very atomized, everything is very like individual and discrete. But really, when you program in C, you can understand that it's all kind of interconnected, and these high-level abstractions that we build on things rely on underlying things that you can actually understand.